All right, our chapter breaks down into 3 sections: scientific method, units of measurement, and using scientific measurements. We're going to start with section 1, and I'm going to introduce a few things a little early so we can just get a warm-up on them. Next chapter. Why is this doing this? There we go.
It's okay.
Uh-huh. Here we go. Move it. We
Just mess up, that way we can laugh.
Yeah. Okay. Our objective is to describe the purpose of the scientific method, to distinguish between qualitative and quantitative numbers, and to describe the difference between a hypothesis, a theory, and a model. Okay. Here we go. Scientific method. Okay. What is a scientific method? Basically, you're observing, and what that means is you use the senses to obtain information. Your observations need to come from your senses, either eyes, ears, or your mind. Your data may be qualitative or quantitative. Qualitative is a description. You think of the word quality. What does quality mean? Well, I know what quality means. How do you describe it? Can somebody describe quality for me? Basically, qualitative means this is a round object. I observe that it's a hot day. I observe that this is quicker than this. I observe something that's not a number. Quantitative is a number. In chemistry, often we're interested in numbers. A lot of the times it's about numbers. A system is a specific portion of matter in a given region of space that has been selected for study during an experiment or observation. Basically, what that means is whenever it says consider the system, it means consider this particular isolated set of events and ignore everything outside of it. So the system you're looking at right now is the computer screen. That is the system. But it doesn't include the air blowing around you or the seat you're in. It's whatever system is defined. Okay, so a hypothesis basically is an explanation that you can test. If I observe a couple things, let's say I observe that the ball in my hand falls when I let go of it over and over again, my hypothesis might be there's a force called gravity pulling it down to the ground. That's a hypothesis you can test. Another famous hypothesis was gravity accelerates all objects the same. And Galileo had that famous hypothesis, and he tested it by taking a very heavy cannonball and a not so heavy ping pong ball, tennis ball, 2 different size objects, and he dropped them from a very high tower, and he watched and they landed on the ground at the same time. And if you do that with a basketball and a ping pong ball or a bowling ball and a marble, they'll both hit the floor at the same time, irregardless of how heavy they are or how much mass. That was a hypothesis that you can test, an explanation of observed events. There are often if-then statements. If such and such happens, then I think such and such will happen. So if I put the cat in the microwave, I think it's going to get really noisy and gross and blow up. You can test it. I know that's pretty gross. But okay, so let's check out this graph, and let's look at it for a few minutes and see if you can come up with a hypothesis. So one thing you could say is like, yeah, if you have more phosphorus in your soil, the plant will grow faster. You might also say, if you exceed 50% phosphorus in the soil, the plant won't grow any faster, because you can see here that the 25% line and the 50% line are right about the same. And so that's just, here's your observation, and then the hypothesis is what you make of that data. Let's move on. Skip that. Testing a hypothesis. This is an experiment. After you observe, step 1 of the scientific process, and then you hypothesize, step 2, then you test, and that's the experiment. An experiment requires that data, a hypothesis, you must have data to support your hypothesis, or else it's worthless. So you're going to need an experiment with controls and variables. Controls are the experimental conditions that remain constant. Probably want to write that down. And variables are any experimental conditions that change. Okay? So I'm going to go back a slide, and we're going to ask a question here in our graph. the growth, time, and phosphorus. The control, the variables that didn't change, would be time. Sorry, never mind. The control would be the plant itself. We had 3 different kinds of plants, but they were the same plant, the same kind of tomato plant, the same kind of corn plant. That would be the control. Okay, variables here would be the time, the growth, how high it grew, and how much fertilizer you used. They all changed. Time changed, growth changed, and fertilizer changed. So after you do an experiment and test your hypothesis to see if it's right or wrong, then you state right or wrong, and then you communicate it to the public in journals or in papers or whatever. Okay, let's move on. Theorizing. A model in science is more than just a physical object. It is often an explanation of how phenomena occur and how data or events are related. A model can be just as simple as an explanation on a piece of paper. In fact, your book is one fat model of chemistry. In many different pictures and many different texts, it's a model of chemistry. It's usually visual, verbal, or mathematical. An example would be the atomic model of matter. Yeah. A theory is a broad generalization that explains a body of facts or phenomenon, the atomic theory. Another way to say that is a theory explains a set of observations. The atomic theory talks about electrons, it talks about observations about neutrons and protons, it talks about the nucleus, it talks about different forces that are in the atom. These are all kinds of observations that many experiments have shown, and it all comes together in one theory. The theory of gravity is another one. Any questions about theories and models? Danielle? It's okay, I want to answer this one.
Okay, theories are like the ones that aren't proven, correct? Or
Okay, a theory technically is never proven. A theory basically is something that is our best answer so far. Later, we might get a better theory, and we can replace it. Right. A repeatable experiment might be a proven observation. It's proven that if you have these conditions, this will happen. And that's proven. So I can prove that at sea level, a ball will drop at a certain rate of speed every time. But the theory of gravity is why. And that's not proven. Yeah. So here we go. Here it is. Here's the breakdown of the scientific method. And what do I want you to know? I want you to know kind of the flow of these main events. First, you observe. You observe and you see what's happening in your world. Then you formulate a hypothesis. If such and such, then I think such and such will happen. After that, you come up with an experiment or a test to see if your observation, your hypothesis is correct. After that, you theorize, meaning after many observations and experiments, you construct models, you try to predict what will happen in a new situation, and you communicate with people. And after you come up with that, then you can publish your results and become super famous scientist. Some people like to try to skip some of these steps to become famous. For example, there was a Korean scientist who skipped the testing and communicating, skipped the testing and said that he could clone a certain kind of stem cell. This is a couple years back. He became super famous because people were really excited, because then you didn't have to use embryos and you didn't have that whole problem anymore. But it turned out he really didn't do the experiment, he lied about it, and he got famous, but then when people tried to reconstruct his experiment, they failed. So you can't skip the theorizing part. Yep. So communication is really important. See how it says 9 minutes and 27 seconds? Don't let me get to 10.